Okay, in chapter 13, section 3, we're going to look at arc length and curvature. So we'll have different equations for these things. So let's take a look. The first part says, you'll watch this video and he'll talk about curves and things like that. He'll say the curvature of a curve R of S, where S is the arc length parameter. It is the magnitude of the derivative of the tangential function with respect to S, and that is true. And in 2, you'll watch this short video and he'll talk more about these concepts. Encourage you to watch it. And another way you can write curvature is the derivative of the tangent function divided by the derivative of the original function. Well, that turns out to be r prime cross r double prime over r prime of t magnitude cubed. And we'll actually see these equations later on. That one's also true. So kind of gives us 2 equations that we can work with to do some of these problems right off the bat. Okay, so the first problem says find the length of the curve. And it gives us a vector function with parameter t, and it's in I, j, and k form. So what we need is the length equation. The length equation is the antiderivative from a to b, which will be in our case 0 and 1. So it's how does t vary? And it's going to be the square root of the derivative of f prime of t squared plus the derivative of g prime of t squared plus the derivative of h prime of t squared with respect to t. Okay, but f, g, and h are just the equations in front of I, j, and k. So 7 is f, t squared is g, t cubed is h. So if f of t is 7, f prime of t is 0. If g of t, in this case, is t squared, g prime of t is 2t. H of t is the equation in front of the k part of the vector. It's t cubed. Therefore, its derivative is 3t squared. Okay, so now we're going to square those things. So the length goes from 0 to 1. Square root of 0 squared plus 2t squared plus 3t squared squared. This is going to equal the antiderivative from 0 to 1 of the square root. 0 squared goes away. You're going to get 4t squared plus 9t to the 4th. And we can factor out, how do we want to do this? Yep, we're going to factor out a t squared, and it'll come out of the square root as a t, and you'll be left with 4 plus 9t squared dt. Better show that step. So what we did was we said, oh, I can factor out a t squared from these 2 terms. So you get 4 plus 9t squared. And then this t squared comes out of the square root as just a regular t. Squared goes away. And you're left with the bubble 4 plus 9t squared in the square root. Now to do this antiderivative, you have to let u equal the inside stuff of the square root, and du is going to equal the derivative of this, which is 18t dt. Therefore dt actually equals du over 18t. And we plug all that back in, and we're going to get t times the square root of u times dt, but dt is really du over 18t. And these t's will cancel, one on top, one on bottom. And this 18 I can pull out front. Oops. It's 1 over 18, not 18, because this is in the bottom. So 1 over 18, antiderivative 0 to 1, u to the 1/2 du. The antiderivative of u to the 1/2 would be u to the 3/2 over 3/2. So add 1 to that. So this would be 1 over 18, u to the 3/2 over 3/2. And the du goes away, and we're still integrating 0 to 1. Well, this is going to equal 1 over 18. This is really like multiplying by 2/3. So you're going to get 1 over 18 times 2 over 3 is 1 over 27. And we're going to replace u with what it was, 4 plus 9t squared, all raised to the 3/2 from 0 to 1. When you plug 1 into this, we're going to get 1 over 27, 4 plus 9 raised to the 3/2 minus, plug in 0, we're going to get just 4 raised to the 3/2. And this becomes 13 to the 3/2 and 4 to the 3/2, and I'm going to cut to the chase. If you do this, you're going to get 13 root 13 minus 8, and both of them are on top of 27. So this, let me actually right here. This is going to be 13 square root 13 all over 27 minus 4 cubed, which is going to be, well, the square root of 4 is 2, and then 2 cubed is 8. So you're going to get minus 8 over 27. And that's going to go right here. So nothing overly, I mean, it's just derivatives and squaring them and antiderivatives. This is all Calc 1 stuff. So we're just plugging it into the only new thing, which is this formula here. So this length formula has to deal with these vector equations. Okay, problem 4, let C be the curve of intersection of the parabolic cylinder, x squared equals 2y, and the surface 3z equals xy. Find the exact length of C from the origin to the point 5, 25, 2, 125 over 6. So, looking at my notes here, we're going to let x equal t. So let's just let x equal the parameter t. Then from this equation here, solving for y, y would be 1/2 x squared. So get rid of that 2 in front of the y by multiplying by 1/2. But x is really t, so y is 1/2 t squared. Okay, then from this one, z, same idea, 3z equals xy, so z equals 1/3 xy. But x and y are both these functions of t. So z is going to equal 1/3 times x, but x is really t times y, but y is really 1/2 t squared. So z is going to equal 1/6 t to the 3rd. Okay, so that's going to be our parametric equation. And so we're going to have r as a function of t is t, 1/2 t squared, 1/6 t cubed. And we need to find the derivative of this. So r prime of t, derivative of t is 1. Derivative of 1/2 t would be bring the 2 down, cancels with the 1/2, so it's just t to the 1st. Derivative of 1/6 t cubed, bring the 3 down, makes that 1/6 to 1/2. Subtract 1 from t to the third, so it becomes t to the second. Okay, now there's another formula that says this. The length of the curve can be written as the antiderivative. Let me think about this one. How do we want to do this? Okay, the length can be written as the antiderivative from a to b of the magnitude of the derivative of the vector equation with respect to t. Okay, and we have that derivative. And the magnitude just says the same thing we wrote in the last one. It says take each of these components squared. So L is going to go from a to b of the square root of 1 squared plus t squared plus 1/2 t squared squared dt. And we are going to get this is the square root of 1 plus t squared plus 1/4 t to the 4th. Now this is actually going to turn out to be a perfect square. So we can rewrite all of this as 1 plus 1/2 t squared squared. So if you were to FOIL this out, you would get 1 times 1, which is 1. You get 1/2 t squared plus 1/2 t squared, which is 1 full t squared. And then your third term would be 1/4 t to the 4th. But this is being squared. So we have a square of something squared, and those are going to cancel. So our length is, let's find out what a and b are before we go too far. Okay, so it says the origin. So the origin would be t equal to 0. So our a term is 0. And then this point, what's this point? Well, if you look at the vector t 1/2 t 1/6 t, this t equals 5. So this would be, this point is t equal 5. And you can check the other points. So if t is 5, you get 5 for the first term. 1/2 times 5 squared, which would be 25 over 2, which is the middle term. Then you get 1/6 t to the third. 5 to the third is 125, so you get 125 over 6. So those line up perfectly. So this second point is 5. Now this square root and this square will cancel, so it's just 1 plus 1/2 t squared dt. And we can perform this antiderivative, no u substitution needed. This is going to equal t, so the antiderivative of 1 is t, plus the antiderivative of 1/2 t squared is 1/2 t cubed over 3, and that's going from 0 to 1. So we get, plug in 1, you're going to get 1 plus, this is really 1/6 times 1, so it's 1/6, minus 0 plus 0. So the, oh, what am I doing? 1. This is 5. Sorry about that. So it's going to be 5 plus 5 cubed, which is 125 over 6. This is a 5, not a 1. And this one's still 0. So you get the length is equal to 5 plus 125 over 6. Put that 5 over 6 by making it a 30. The length will be 155 over 6. Right there. Okay, so another way to calculate length, if you've got the vector equation, take the derivative and then take the magnitude of that. Okay, problem 5 says, show that the curvature of a circle of radius k is 1 over k. So for a circle, we have the vector equation should be any k, which would be the radius, times cosine plus the radius times sine. And we know from previous examples, we've seen this a couple times, if we square those, we get k squared cosine squared plus k squared sine squared, and cosine squared plus sine squared is 1, so you get the radius is radius squared is k squared. Okay, so we take a derivative of this. The derivative of cosine is minus sine, and that k is there for the ride. The derivative of sine is cosine, positive, and the k is there for the ride. So that's the derivative. Then we're going to calculate the magnitude of this derivative. So the magnitude of this derivative would be minus k sine t squared plus k cosine t squared. So we're just squaring each component of the derivative, adding them up, and then square rooting them. That is the magnitude of something, some vector. But this is going to be k squared. So minus k squared is positive k squared times sine squared t plus k squared times cosine squared t, all square rooted. And we're going to factor out k squared, which gives us sine squared t plus cosine squared t. And that whole thing, as we've seen many times now, is 1. So it's 1 times k squared, which is just the square root of k squared, which is k. So we've just proved that the magnitude of this derivative is k. Then they say the tangent vector is the derivative vector divided by the magnitude of the vector. So we're just taking this vector divided by its magnitude, which is k. So that's going to get rid of all the k's. And you're just left with minus sine t and cosine t. So that's the tangent vector. Then the derivative of this, derivative of minus sine would be minus cosine. So derivative of sine is cosine, but the minus will stick around for the ride. Derivative of cosine is minus sine, so we pick up a minus sign there. Then it says prove that this equals 1. Well, to prove that the magnitude of that vector equals 1, I just have to square both components, add them together, and square root them. But this is just going to be the minus signs will go away. This is cosine squared t plus sine squared t. And we've already seen that that is just 1, so it's the square root of 1, which is 1. Okay, so we proved that one. Now it says the curvature is the magnitude of the tangent, the derivative of the tangent vector, divided by the magnitude of the r vector. We know the magnitude of the tangent vector derivative is 1. We just proved that. And we know the magnitude of the r vector derivative is k. We proved that. So the ratio of that's just 1 over k. So that's the curvature value. It is the magnitude of the tangent vector derivative divided by the magnitude of the actual radius vector derivative magnitude. Okay, and we get the constant 1 over k. Okay, so 6 is going to actually have us calculate a curvature, and we're given an r vector. So let me see how I did this one. Sure, we can do it that way. So I use this formula. You don't have to use this one. You can use whatever one you want. I use the curvature is equal to we just saw it in the last problem, the magnitude of the derivative of the tangent vector divided by the magnitude of the derivative of the radius vector. And we saw in a problem 2 I think, that from the video, that can be written as the magnitude of the derivative vector crossed, oops, it's a derivative there, crossed with the second derivative of the vector equation, all divided by the magnitude of the derivative vector cubed. And it's not too bad in a problem like this to find the derivative of the vector and the second derivative. So the derivative of this vector would be 7, and let me not write the i's, j's, and k's. It's going to be 7, 7, and 2t. Which means the double derivative, the second derivative, is just going to be 0, 0, and 2. Therefore, I will show this, I haven't shown in a while, r cross r prime cross r double prime, this numerator, is going to equal the cross product of 7, 7, 2t, and 0, 0, 2. Well, that's going to equal, cover up the first column, 7 times 2, which is 14, minus 2t times 0, which is 0 in the I, minus, cover up the middle column, 7 times 2 is 14, minus 2t times 0, which is 0 in the j, plus, cover up the third column, 7 times 0 minus 7 times 0 in the k. So the r cross r prime cross r double prime vector is 14, 14, 0. And the top says I need the magnitude of that vector. So the magnitude of r prime cross r double prime is the square root of 14 squared plus 14 squared plus 0 squared, which equals 14 square root 2. Okay, that's the top. Now the bottom requires us to find the magnitude of just the r prime vector and then cube it. So the magnitude of this would be, r prime was 772t, so it's going to be 49 plus 49 plus 4t squared. And we're going to have, this is equal to the square root of 98 plus 4t squared. That whole thing is cubed, so that's the same as 98 plus 4t squared raised to the 3/2. Okay, so this is going to go on the bottom, and the tangent vector magnitude is going to go on top, like so. So it's just the ratio of those two things. So we reviewed cross product and derivative and second derivative and fractional powers. Okay, in 7 it says find an equation of a parabola that has a curvature 8 at the origin. Okay, so for 7 we're going to have that we have a parabola. So we're going to say, okay, I don't know what the function is, but it should be some ax squared, because that's what a parabola is, where a is bigger than 0 because it opens up. So when it says opens up, that means the number in front of your x squared term of your parabola is positive. Okay, now we're going to find f prime of x, which would be 2ax. Then we're going to find f double prime of x, which would be 2a. And the reason we're doing this is because we can also calculate curvature via this equation. It's the magnitude of the second derivative of x divided by 1 plus the derivative of x, boy this one's tricky, squared, and all that's raised to the 3/2. Okay, so we have the magnitude of the second derivative of x is going to be the square root of 2a squared, so it's going to be the exact same thing. So we're going to get 2a out of that. And f prime of x we have as ax squared, so let's plug in everything we know. This would be 2a, and this would be 1 plus the derivative squared. The derivative is ax squared, but if you square that, you're going to get a squared x4, and then that's raised to the 3/2. But it tells us that this derivative has to equal, this curvature has to equal 8. So this equals 8. And it tells us that this occurs at the origin. Well, the origin is x of 0. So if we plug in x of 0 for this left side, you're going to get 2a over 1 plus 0, all that goes away, raised to the 3/2. Well, 1, so that just becomes 1. 1 to the 3/2 is just 1. So this says 2a over 1 has to equal 8. So 8 equals 2a, therefore 4 equals 1a. So all of that, plug this a back into the original equation that we guessed at. So we guessed that this was ax squared, but we know a is 4, so the original function had to have been 4x squared. We could calculate that knowing its curvature and that it started at the origin, and using this formula that I just introduced. Okay, problem 8 is a DNA molecule one, and so we want the length of the DNA molecule. So it says, so the setup looks like this. The length goes from 0 to this number here. So we've got 2.9, let's see here, times 10 to the 8 times 2 pi because of the helical nature of these, because they have complete turns. So complete turns means 2 pi. Okay, so that's the length, and then it's going to be times the magnitude of r prime of t, dt. But this radius vector, I think it states it in here somewhere. Oh, I guess it doesn't. I have to show it. So, they're 10 angstroms. So the radius of each helix is 10 angstroms. So what we're going to say is, okay, we knew that when we had a circular element, that you could break it down into the radius times cosine of t in the x, radius times sine of t in the y, and then the z component is going to be this right here. Each helix rises about 34 angstroms during each complete turn. So that would say 34 angstroms times the t value divided by 2 pi per each turn. Per each turn is 2 pi. So you're dividing by 2 pi. So that's the radius vector. That's the hardest thing to derive. So once we get that, the derivative is actually not too bad. The derivative of cosine is minus sine, so it's minus 10 sine t. Derivative of sine is cosine, so it's 10 cosine t. And the derivative of 34t over 2 pi is just 34 over 2 pi. Okay, the magnitude of this, however, is going to be it's going to be the square root of each of these terms squared. Now I'm going to kind of skip showing every little step. I'm going to square each of these 3 terms in the r prime of t. So it's going to be 100 sine squared t plus 100 cosine squared t. My pen is quickly giving up on me. Plus 34 over 2 pi squared dt. But this is just going to be 100 because sine squared t plus cosine squared t is 1. And if you factor out the 100, you're going to get, this is 0 to, let me just call this whole thing capital B, so I don't have to keep writing it. This is going to be the square root of 100 plus 34 over 2 pi squared. That's just a constant. That whole thing is just some number. So I can pull that whole thing out of the derivative, or I can just take the derivative of this being a constant. So this is just equal to the antiderivative of dt is t. So it's the square root of 100 plus 34 over 2 pi squared, some number, times t, where t has to be evaluated from 0 to that b number, which I'll write it back in, was 2.9 times 10 to the 8th times 2 pi. So really all you have to do is take this square root number times this top number, because when you plug in 0, the whole thing goes away. So to get this answer, you're just going to take whatever this number is times this number here. And you should get 2.07 times 10 to the 10 angstroms, which is about 2 meters. Okay, so I believe, yep, that's all you need for that one. Okay, a couple true false, those are always nice. Suppose f is twice continuously differentiable at an inflection point of the curve y equals fx, the curvature is 0. So an inflection point occurs when the graph goes from concave down to concave up. So this right here is called an inflection point. Now, the derivative of this is a flat line. Yeah, let's look at the derivative. The derivative of this is a flat, straight line that has no curvature. So the curvature is 0. Yes, it is true. Okay, last one. Determine whether the statement is true or false. If the curvature is 0 for all t, then the curve is a straight line. So that's true as well. So the only way you can have curvature 0 for every single t is if you have any straight line. So any straight line I draw, the curvature of this is, so curvature, now how is this curving? It's not. So this is all k equals 0. 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 Okay, so that one's also true. Okay, and that will complete section 13.3.